So the goal of today is to present the variational quantum algorithms that are a family of algorithms to be run in a supercomputer. In the last session, we explained the algebraic quantum algorithm, so how to minimize, how to find the solution of an integration problem, of a curve integration problem, by finding the ground state of an missing Hamiltonian. In this case, let me just do a bit of zoom out and explain that these algorithms have applications beyond the finding ground states. Although here the mindset that we will have will be using variational quantum algorithms to find to solve an optimization problem. Okay, so they work as follows. So here we have a register of qubits where we will run our quantum circuit. Okay, in variational quantum algorithms, the quantum circuit is parameterized with some parameters theta. And we have to think that this unitary is has an ansatz. Okay, there are many models, many ansatz for these variational quantum algorithms. The example that we explain later will be the QAOA, but we could consider we could design any ansatz, or any structure of the gates. For instance, let me present here an example. We could consider a circuit of only 2 qubits that initially start in state 0, and then we perform here a Harman gate, and here, I don't know, another single qubit gate that is an X rotation of some angle theta 1, and here we performed, I don't know, an Y rotation of some angle theta 2. And then we do control not. Okay, this could be an example of a variational quantum circuit that has 2 parameters, theta 2 and theta 1. Okay. So good. So every type of variational quantum algorithms will have a certain ansatz for the circuit with a series of parameters that will explore the Hilbert space. Noticing that as the initial state is fixed, changing the values of the parameters, what is doing is changing the point where we reach the quantum state that we generate in the Hilbert space. Okay. There is an important property of a circuit called expressivity, and the expressivity precisely tells us which volume of the Hilbert space we are able to reach by means of the circuit. Okay. Good. So this is one element that we need: the ansatz and the quantum circuit. Okay. So when we apply this quantum circuit to this initial state, what happens is that we generate state C of theta that is basically the application of this unitary to the initial state that is the product of zeros. Okay, and then the next step is to evaluate the cost function. So what is the cost function? In our case, the cost function, because our goal will be to find the ground state of an Asian Hamiltonian that comes from a QO problem. In our case, the cost function will be just the expectation value of the problem Hamiltonian. Okay. The cost function could be more complicated than this. It could have a sampling over different possible initial states, and so it could be different. In our case, we take this one. that we require is that it can be efficiently computed, no? That is computable. In the sense that what we will do in the lab is that we will run the circuit, and at the end we will perform expectation values of operators. So we need that by performing expectation values of operators, we can estimate this cost function in a polynomial time, in a polynomial number of operations. This is indeed the case for the type of Hamiltonian that we had, because remember that the Hamiltonian we had was an easy Hamiltonian, right? It was a Hamiltonian of this type that we had. So we had one body operators and two body operators. Okay, so basically we have n squared of this, n operators of this type, and therefore it's polynomial, therefore that we need to compute this cost function. If the cost function is different, so we should, okay, one thing that we should take into account is that this condition is fulfilled, that any cost function we want to estimate in order to run a variational quantum algorithm is computable. Another condition that we need is that indeed in our case the problem we're going to solve is finding the ground state of this Hamiltonian. What we need is that the minimum of the cost function, so the thetas that attain the minimum of this function will correspond to the minimum of the so that let's say that the ground state that we would like to achieve is in the region of expressivity that this circuit allows you to reach. Okay, so I would say that the minimum of C corresponds to the solution. No? Corresponds to the solution. Even, okay, if this condition is not fulfilled, at least we would like to have, because sometimes we don't know how, if the ground state is contained here. But one thing that we like then is that the cost function is operationally meaningful. In the sense that, okay, that states that give you better values for the cost functions are better solutions for your problem. Okay, that there is a kind of correspondence. In this case, for this wave function, it's obvious that this is the case. No? Although that we have this equation here. But for other cost functions, it's not so clear. Good. And then there is a last condition that we can would like that we would like to have, but okay, it's not clear that we will always have it. And this last condition concerns about the classical element of the variational quantum algorithms, that is the optimizer. Okay, basically the algorithm works in this way. So we have the initial state, we run the quantum circuit, we will have to run the quantum circuit several times because we will need to compute several expectation values in order to estimate the value of the cost function for these given parameters. So here we perform a measurement. Okay, and then the idea is that with the results, with the estimation that we have, we use, say, an optimizer, a classical optimizer. And the role of this optimizer is just to propose some new parameters to try to find a better value of the cost function. Okay. So as basically many of these classical optimizers are used based gradient methods. Sometimes when we measure here, what we want is not computing explicitly the cost function, but what we want is computing directly its derivatives. So given we could perform the derivative of this cost function with respect to every of the parameters, and we would obtain here an expression that we would evaluate in this measurement process. Okay, but this will depend on the type of optimization that you use. Sometimes you compute, so you with the measurements you estimate the derivative of the cost functions, and some other time, depending on the result that you use, you will compute explicitly the cost functions. But the idea is that you iterate this process of determining the cost function or its derivative, then passing these values to classical optimizing, proposing some new values, running the procedure again, and we repeat this operation until with the problem converge and finds a minimum. And this minimum is the solution of the variational quantum algorithms produce. And here, so as we are using here a classical optimizer, one other condition that we will need is that the classical optimizer is trainable. The classical optimizer. Okay? In the sense that sometimes, and we will see some examples, this problem could be, so the classical optimizer could perfectly got trapped into some local minima. So, so your problem is very difficult. Usually, what this difficulty is manifested in a variational quantum algorithm by getting trapped in the classical optimizer. Okay. So I will try to summarize what's a variational quantum algorithm. So basically, it's an algorithm in which we have a secret that depends on some answers and some parameters. So the more gates you have and the more big is your circuit, more expressibility will be your wave function. So you will, this wave function here will be able to explore a larger region of hyperspace. Okay. Then with this wave function, we estimate the expectation value of the cost function or the cost function or its derivatives, depending on the classical optimizer that we use. Then a classical optimizer decides and proposes some new values for the parameters, and the process starts again. Okay, until the cost function is minimized and some value is attained. Okay, so this is the structure of a variational quantum algorithm. And now I would like to explain some limitations that we find when we deal with variational quantum algorithms. So this condition on the tunability is actually will have implications on the performance of these variational quantum algorithms. Okay, let me introduce first to develop more in this tunability notion the idea of energy landscape. So the energy landscape basically is just to understand that when we given an answer, in a certain number of parameters, you assume that we have n parameters. Then this cost function is a function of r to the m to the reals, right? So we assume that these are real function, and then we have n parameters of lambda. That in this case we assume that they are continuous. Okay, if they are not continuous, then the same notion applies, but it's a bit more complicated. So let's assume that okay, basically we can understand the cost function as a function that goes from a space R to the n to real, right? So basically this is the energy landscape. And if we had one parameter, so one possible energy landscape would be this one. We had only one theta, so we would have this one. Okay, and okay, go to higher dimension, so the energy landscape becomes more and more complicated. Okay, so the main limitation of these variational quantum algorithms comes from two facts. So one possibility is that the energy landscape has many local minima, and the classical optimizer is not able to find the global minimum, the global minimum. Okay, so this is something that that could happen, and that then the model is not. We say that the model is not trainable, and we're not able to reach the ground state and solve the problem. So let me say this that we have many local, okay, there's many property. And another phenomenon that limits the trainability, and it has kind of interesting implications concerning the nature of the problem, is the existence of the so-called barren plateaus. So the barren plateaus, it's what happens to the energy landscape of the cost function when in some cases, when we increase the system set of the system, so when we add more qubits and run the rational quantum algorithm, and the energy landscape becomes flatter and flatter, and so also do the derivatives, okay? And then what happens is that the precision that you need in order to discriminate towards which direction you have to go in order to look for the minimum is very high, because all the values are very close to each other. Okay, so this in practice what happens is that requires exponentially many measurements in order to discriminate between these different directions that you can take to see which is the one that allows you to find the minimum, and then makes the method applicable because it becomes just inefficient. So if we want this limitation for plateaus, it's not a limitation because of the classical optimizer isn't able to find a way, but because we need exponential many measurements to discriminate in which direction we have to go. So we evaluate the condition of computability of the function that we were mentioning before. Okay, so it turns out that the barren plateaus are a consequence of having vectors in the space that when they overlap, so basically they are two vectors. So these small differences in different values of theta correspond that to the overlap of different vectors being always very small. Okay, and this is a consequence of the huge dimension of the Hilbert space. Okay, so the Hilbert space increases the size of the Hilbert space, the dimension of the Hilbert space increases exponentially with system size, and therefore when we just take two random vectors in the Hilbert space, basically its overlap is zero, and here we can understand this as a type of overlap. And so this is the origin of the barren plateaus, and then there are some works indicating that there is a connection between if you want, the existence, so the absence of barren plateaus, so there's a connection between the absence of barren plateaus and the classical simulability of that system. Okay. Well, so in this section, what we have seen is that we have introduced the main elements that form the variational quantum algorithms. So the ansatz of the circuit with its parameters, the measurement that we need to do to estimate the cost function, that will be the crucial quantity of this business. Also, the classical optimizer that suggests new values for the parameters in order to find the down state. And also, we have reviewed which are the main limitations of these ambient methods. Okay. In the next section, what we need to do is just present a particular case of variational quantum algorithms. That is the QAOA, which is maybe the most popular variational quantum algorithm used in the literature. And we will see how it can be related with the adiabatic quantum computation and how it can be used to solve optimization